Hello, 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 everyone. Welcome back. We will be going into section 7.3 for this deep dive into chapter 7 for module 4. And in this section, we're going to be looking at this concept of proportions and how we're going to be estimating population proportions given sample proportions. Okay, so in the previous section, we talked about how we can use a sample mean to estimate our population mean. But sometimes when we're working with some data, it doesn't really make sense for us to calculate a mean. And sometimes there's no way to even calculate a mean to begin with. So what do we do in those situations? If we're working with categorical data, which is a really big application in this section, we're going to be working with proportions, okay? So again, we're talking about that categorical data and also any data that may not be inherently numerical, okay? So in our population proportions, we're going to be looking at our target characteristic, but then we're also going to be considering the other portion of our data set that does not have our target characteristic, okay? And that's going to be known as Q. The first one, the proportion that has our target characteristic is going to be P. Okay, target P does not have the target Q. Okay, so we can use we can use estimates based off of our sample proportions. So we can think about these sample proportions as the point estimates for our population proportions. And that's going to be P with a circumflex, also known as P hat, and Q with a circumflex, also known as Q hat. And these sample proportions are going to be represented in the following equations, where P hat is equivalent to R over N, and Q hat is equivalent to 1 minus P hat. Okay, so looking at that second equation there for the Q hat, we can see numerically that Q hat is going to be our complement of P hat. And that makes sense because if you don't have the characteristic, the only option is that you do have the characteristic and vice versa. Okay, and if we're looking into the first equation a little bit more, we see that R is representing the number of successes or individuals with that target characteristic, and N is that sample size, okay? So we're looking for the proportion of people who have that characteristic that we have in mind here, okay? The margin of error, that sort of like ambiguous, that more theoretical equation that we talked about in sample 7.1 can also be seen similarly for the margin of error for our populations, for our proportions, where we're comparing the population proportion to our sample proportion. And that's going to be the magnitude of the difference of these two, okay? But similar to the 7.1 where we looked at the margin of error for the means, it doesn't really make sense for us to consider the population proportion in here, because if we knew the population proportion, there's no need for statistics. So we're going to have to look at how we can conceptualize the margin of error based off of just our samples, okay, and creating that maximal margin of error. Okay, so it turns out that if we take the distribution of our p hat values, we can approximate them to the normal distribution as we get a larger and larger sample size. Okay, so that's sort of going into that that central distribution theorem that we talked about in a previous chapter there, okay? As our samples increase, we start to see that we start to get closer and closer to our normal distribution. That's happening here with our p hat values, okay? And as we display the distribution of our p hats in this fashion graphically, we start to see the following characteristics, where our mean is going to be equivalent to that population proportion, or that population proportion. And our standard error is going to be represented in this equation, where we have the fraction, where the numerator is going to be the product of p hat and q hat, and that's going to be divided by our sample size. And all of that is going to be underneath the square root, okay? So just to show a little bit of what I mean here for clarification, okay? We are going to see an approximate normal distribution for p hat, okay? So when we're talking about mean, we're not talking about a numeric mean. We're sort of looking at, no, not necessarily numeric mean, but like the average mean that we're talking about, like where we add everything divided by it, by the sample size. Here we're talking about that proportion. But when we're talking about mean visually, we're talking about it being like that middle part of our normal distribution curve that's being approximated, okay? So I wanted to make that a little distinction there, that we're not just magically getting some kind of mean when we're doing proportions, okay? So because this distribution starts to become so it starts to look more Gaussian and normal, okay? We can abuse that property to derive the maximal margin of the error. So here, again, we're looking at this general kind of idea where we're taking the critical value and multiplying it by our standard error, okay? So that's exactly what we have here. Our critical value multiplied by our standard error, which is what we found in this equation above, okay? And here, I did not bother with the details of the derivation. It's going to look similar to the derivation that is outlined in 7.1, okay? And this next part of the section is that we're going to actually compute and interpret these confidence intervals for p, okay? So if we recall, when we talk about confidence intervals, we're talking about the boundaries that we set that's based off of the confidence level that we choose, as well as our margin of error. So we're going to use this margin of error equation that we just outlined above, as well as this critical z-value, so that we can find this confidence interval, so that we can start to build a picture on where exactly our population proportion may be, okay? So here it's going to be similar to how we did it with our means, but we're using our proportions. So we're going to add and subtract our margin of error to find those middle parts, okay? And just for completeness, I'm going to show it in that other fashion as well. So we took the p hat and we subtract our margin of error. This should be less than our population proportion, and that population proportion is going to be less than p hat when we add our margin of error, okay? So this was an equation that we sort of saw in 7.1. I just wanted to reiterate that that's going to be a similar characteristic that we see in our sample proportion calculations, okay? So everything that we have here in the curly brackets is going to be similar to what we see here in that first line equation, okay? And in this second equation that we have here, what we're doing is we're taking our margin of error equation that we have above here, that I'm going to be breaking or bordering in green here, and we're plugging it into the equation, okay? So our final equation that I'm going to be highlighting here in yellow is going to be p hat plus or minus the critical value multiplied by the square root of the product of our sample proportion and the complement over the sample size, okay? And in the next video, we're going to do a example where we calculate not only the margin of error, but also the confidence interval.